Now let's do one example. We have a steam Rankine cycle with superheat and reheat. Superheat and reheat. So we will have two turbines. Steam enters the first stage turbine at 8 megapascal and 480 Celsius, so that is P1 and T1. Leaves the first stage turbine at zero point 0.7 megapascal, and then reheats to 440 Celsius. Leaves the second stage turbine at 0.008 megapascal. W dot cycle is given as 100 megawatts. We're looking for three things. First, sketch the process on a T versus S diagram. Second, look for the efficiency. And the last one is to look for the mass flow rate. Okay, so let's start from the first part. Sketch the process on a T versus S diagram. We will have a viridome first. And then let's sketch the first constant pressure line. We will have three constant pressure lines, 8 megapascal, zero point 0.7 megapascal, and 0.008 megapascal. So let's sketch three of them. Okay, so the top one should be 8 megapascal, and the middle one should be 0 point 0.7 megapascal, and the bottom one should be 0.008 megapascal. Okay, and let's start from number 1. Locate point 1. How do we locate point 1? Essentially, you're asking yourself, what is the phase of number 1? What is the phase of number 1? We know P1. Steam enters the first stage turbine. That is point number 1. Point number 1 has a pressure of 8 megapascal and a temperature of 480 Celsius. How do we fix the state of this point number 1? We do the same as before. We go to table A3. We start from pressure. P1 is equal to 8 megapascal, which is 80 bar. And from the table, we can easily find saturated temperature. We call it Tsat1, and it's 295.1 Celsius. Okay, our actual temperature T1 is 480 Celsius, which is greater than saturated temperature. So the conclusion is point 1 must be superheated. So next question is, where do I put point number 1? Point number 1 must be on this 8 megapascal line, and it has to be superheated. But is that enough for us to fix the location of number 1? So for example, if I put number 1 here, it satisfies the requirement to be superheated. And then when I sketch 1, 2, 2, which is the first stage turbine, I go straight down. And then the problem says leaves the first stage turbine at 0.7 megapascal, so number 2 must be on this 0.7 megapascal, which is here. Or can I actually put number 1 right above G point? Can I put number 1 here? And then when I go straight down, number 2 will just be G point. Or possibility number 3, can I put number 1 further to the right? And then when I go straight down, point 2 will end up as superheated water vapor. Yes, all three scenarios are possible, so we need to find which one is correct. Do you remember how we did it before? We find a reference line. Okay, how did we find a reference line? we choose this G point. We choose this G point, and this point we call point 2G, and we draw a vertical line across this point as a reference line. The x coordinate of this point is S2G. And then what we do is to find S1 and S2G. If S1 is less than S2G, then you must put number 1 to the left of this reference line. If S1 is equal to S2G, then you must put point 1 right on this reference line. And if S1 is greater than S2G, you must put number 1 to the right of this reference line. Okay, so next is to look for S1 and S2G. How do we look for S1? We know number 1 is superheated, so we must go to table A4. And the two inputs we have are pressure and temperature. And from the table, we can easily find S1. In the table, I also write down H1, even though I'm not looking for H1 at this moment. 3348.4 kilojoule per kilogram. You want to write down the enthalpy of every single point because remember, the key of solving any Rankine system is to look for the enthalpy of every single point. So you want to write down H1, H2, enthalpy of every single point. Okay, so now we have S1. The next one we're looking for is S2G, which is our reference. How do we look for S2G? What do we know about point 2G? We can take a look at the diagram. Point 2G is on the constant pressure line, and the pressure is 0.7 megapascal. We start from pressure and go to table A3, then we can easily find S2G. P2G, pressure of point 2G, is equal to 0.7 megapascal. And from here, we can find from the table S2F, S2G, S2F is 1.9922. P2G is equal to P2. And S2G is 6.7080. And then, just like I said, you want to always write down enthalpies. We write down H2F and H2G. So now I have S1 and S2G. So we can do the comparison, which one is actually bigger. S2G is actually bigger. S1 is less than S2G. So what is our conclusion? Point 1 must be to the left of point 2G. So now we go back to the diagram, and we must put number 1 to the left of this reference line. So for example, somewhere here. This is number 1, and then locating point number 2 will just be very easy. You just go straight down because 122 is the first stage turbine. That is an isentropic process. We go straight down and down to 0.7 megapascal because the problem says steam leaves the first stage turbine at 0.7 megapascal. So 122 done. That's our rule, 122. Okay, how did we locate point 2? Very easy, 122 vertical because it is isentropic. Okay, so we're done with point number 1 and point number 2. Next, let's locate point number 3. What is 223? 122 is the first stage turbine. After the first stage turbine, you send the steam back to the boiler. So 223 is going through a boiler where you gain heat again. If you gain heat, you also gain entropy, so you must move to the right because entropy is the x-coordinate. And in a boiler, it's a constant pressure process, so 223 must be along this zero point 0.7 megapascal constant pressure line and to the right. Okay, when I move to the right, where should I put number 3? Again, you have three possible solutions. I can put number 3, for example, here. Number 3 will still be a mixture. Or I can put number 3 right here, and it's just the point G. Or I can put number 3 here, and then number 3 will be superheated. So which one is it? We can take a look. What do we know about number 3? Reheat to 440 Celsius. So we actually know T3. And what about P3? We also know P3. P3 is zero point 0.7 megapascal. So from pressure and temperature, we can find out what the phase of number 3 is. We know P3, pressure P3 is 223 is on the constant pressure line. P3 is equal to P2, which is 0.7 megapascal, and that is 7 bar. If you start from pressure, you go to table A3. And from here, we can find a corresponding saturated temperature. So we call it Tsat3. And the value is 165 Celsius. What is our actual temperature? T3. Reheat to 440 degree. So our actual temperature for number 3 is 440, which is bigger than saturated temperature. And then again, our conclusion is point 3 must be superheated. Okay, so now let's go back to the diagram. All right, so now we know we must put number 3 to the right side of the vapor dome because we just proved number 3 must be superheated. So number 3 must be somewhere here. And be very careful. Why? Because T1 is given as 480 degree and T3 is given as 440 degree. So T1 is actually higher than T3. So when you sketch number 3, you have to make sure number 3 is a little bit below number 1 because the y coordinate is temperature and T3 is less than T1. So put number 3 below number 1. So let's call this point number 3. This is our point number 3. Okay. Number 3, go to the right, and then 3 to 4. Let's locate number 4. Let's locate number 4. Oh, we're not done with number 3 yet, because remember, 3 to 4 is the second turbine. 3 to 4 is the second turbine. How do we sketch the second turbine? 3 to 4, you must go straight down because it is isentropic again. So is it possible for me to have 3 to 4 where number 4 ends up as a mixture? Yes. Or number 4 ends up as a G point, or number 4 ends up as superheated? Yes, you have three possible solutions. And then how do you decide which one is correct? Do what we did for number 2 again. So what you are going to do is to draw another reference line this time. This is our new reference line. And this is our reference point. Let's call it point 4G. Point 4G. And the x-coordinate of this point will just be S4G. So now what you need to find is S3 and S4G. If S3 is less than S4G, you must put number 3 to the left side of this reference line. If S3 is equal to S4G, then you must put number 3 right on this reference line. And if S3 is bigger than S4G, you must put number 3 to the right side of this reference line. Okay, so now let's look for S3. How do we look for S3? We know point 3 is superheated, so we must go to table A4. And what are the two inputs we know? Pressure and temperature. P3 is zero point 0.7 megapascal, and T3 is 440 Celsius. And from here, you can easily find S3. S3 is 7.7571. And I also write down H3. H3 is 3353.3. Do not forget a unit. So now first I have S3. And what is our reference? Our reference is S4G. Okay, what do we know about point 4G? We know point 4G is on this constant pressure line, which is 0.008 megapascal. So we start from the pressure and look for S4G. Starting from pressure, we go to table A3. Pressure of point 4G is equal to P4, and that is 0.008 megapascal, which is 0.08 bar. And from here, we can find S4F and S4G. And also write down enthalpies, H4F and H4G. So now we have S3 and S4G, which is our reference. Then we can do a comparison between those two numbers. Which one is actually bigger? S4G is bigger. S3 is less than S4G. So what is the conclusion? Point 3 must be to the left of point 4G. So now let's go back to the diagram. Okay, we have a few requirements about number 3. First, it has to be superheated, and then it has to be on 0.7 megapascal line, and also it has to be to the left of S4G point. So it must be somewhere here. This is where number 3 is. Okay, to the left of this reference line. And then again, just like I said before, because T3 is 440 while T1 is 480, so number 3 must be below number 1 since the y coordinate is temperature. Okay, so now we've fixed the location of number 3. You can see it's not very easy, huh? There's so many details you have to pay attention to. And then number 4 will just be very, very easy once number 3 is fixed. Because 324 is the second stage turbine, and then it is isentropic process. So 324 must be a vertical line going down. Down to where? The problem says the second stage turbine at 0.008 megapascal. So you just go straight down till you reach 0.008 megapascal. So we go straight down, and now that's my number 4. And you can see number 4 must be a mixture. Locate point 4. 324 must be vertical. And because the process is isentropic. And number 4 must be a mixture based on our geometry. Okay, and then 4 to 5. 4 to 5 is the condenser. You always cool down to F point. So 4 to 5 to the left. And you reach number 5, which is F point. And then 5 to 6 is the pump. You pump up the pressure to the highest, which is 8 megapascal. So we go straight up, and that is my number 6. And 621 again is the boiler. So now we're done with the whole diagram. 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, and 6 to 1. And now you can see the location of number 2 and number 4. They have 3 possible solutions for each one of them. And how do you decide which one is correct? By comparing S1 with S2G and S3 with S4G. You need to have those 2 reference lines in order to fix the location of number 1 and number 3. Okay, so next question is to look for efficiency eta. Okay, efficiency. Let's start from the definition of efficiency. Efficiency is what you get divided by what you pay. What do we get? What we get is W cycle. And what do you pay? You pay for the heat. And then what we do is copy W cycle. And then for the denominator, this time is different from before. Why? QH is the heat you absorb from the boiler. However, if you have a reheat cycle, you go through the boiler twice. The first time is 6 to 1, and the second time you go through the boiler is 2 to 3. So you need to combine those 2 steps for QH. Okay, so the first one is Q absorbed from 6 to 1 plus the second one, that is the heat absorbed from process 2 to 3. Okay, and then next what we do is to divide every term by time, so it becomes W dot cycle and Q 621 dot and then plus Q dot 223. That's the first step we do, divide every term by time. And then the second step we do is to divide every term by mass flow rate. Divided by mass flow rate, divided by mass flow rate, and divided by mass flow rate. Okay, and why do we do that? Because recall, whenever we look for W over mass or heat transfer over mass, what was our solution always? It always has the same format. If you don't remember, you can always start from first law. But if you can remember, everything will just be quick. The solution is always in the format of the difference of the 2 enthalpies. Enthalpy minus enthalpy. Enthalpy minus enthalpy. It's always this format. And we always use the bigger enthalpy minus the smaller enthalpy, so the solution will always be positive. If you can memorize this format, everything will just be quick because you won't need to go back to first law again. Okay, so now let's continue. Let's continue. The numerator is W cycle per unit mass. What is W cycle? W cycle is the net amount of work coming out of your system. So it must be work generated minus work consumed. So work generated must be W dot first turbine 1 to 2. That's the work generated. However, you have a second turbine, so plus the work generated in the second turbine, that is 3 to 4. So those two terms combined together gives you the work generated, and then subtract the work consumed. The pump consumes work, which is process 5 to 6. So now we have rewritten the numerator. And then let's copy the denominator. It's Q dot 621 over M dot plus Q dot 223 over M dot. Okay, left-hand side is still efficiency. Let's continue. So now we can rewrite each one of them. Let's start from W dot 122 over M dot, this one. What should be the format to the solution? It will always be H something minus H something. The next one, we decide which one minus which one. H1 minus H2 or H2 minus H1. We always use the bigger H minus the smaller h. So which one is bigger? Or in other words, Which one has more energy, 1 or 2? 1 is the beginning of the steam turbine. Very hot steam goes into the steam turbine and then pushes the blades to turn and then it cools down at number 2. So obviously number 1 has more energy. So we should use H1 minus H2. Okay, that's the first one. And then plus the second one, 3 to 4. 3 to 4 is the same, H minus H. Okay, which one is bigger? 3 to 4 is the second turbine. Number 3 is the inlet. Number 4 is the outlet. Inlet must have more energy. Same reason for number 1. Minus 5 to 6. 5 to 6. So again, H something minus H something. Do we use 5 minus 6 or 6 minus 5? Which one has more energy, 5 or 6? 5 to 6 is the pump. You pump up the pressure. You have to provide electricity. So which means from 5 to 6, you add electricity, which is energy, into the system. So at the end, you must have more energy. H6 must be bigger than H5. So we use H6 minus H5. Okay, so now we're done with the numerator. Let's move on to the denominator. Okay, heat transfer 6 to 1. Again, same format, enthalpy minus enthalpy. Which one minus which one? 6 to 1, which one is bigger? 6 to 1, let's take a look at diagram, is the boiler. In the boiler, you gain heat, so you must have more energy at the end. So H1 must be bigger than H6. So we use H1 minus H6. And then the last one, 2 to 3. Do we use H2 minus H3 or H3 minus H2? Which one has more energy? Let's take a look. 2 to 3 is going through the boiler again. So that means during this process, you gain heat. If you gain heat, you must have more energy at the end. So H3 must be bigger. So we use H3 minus H2. So now this is the equation we have for efficiency if you have a reheat cycle. Now take a look at the right-hand side. What do you need? H1, H2, H3, H4, H5, and H6. You just have to find every single one of them, then you're done with this problem. Okay, so let's start from H1. What is H1? We found H1 earlier already from table A4. It's 3348.4 kilojoule per kilogram. If you forgot, let me show you. H1 right here. We found H1 already. Okay, so next one, H2. How do we look for H2? We didn't find H2, so let's take a look. Let's make a plan. If you take a look at this diagram, you can see number 2 is a mixture. So what's your plan to look for H2? You have to have quality X2. Okay, so our plan is I have to use quality. H2 is equal to 1 minus X2 times H2F plus X2 times H2G. You have to use this equation. H2F, H2G, I found those two from the table already. I just need to find X2. How do we look for X2? Same old method. We use a different property. What is the property we use? We use entropy. And now from here, we rewrite this equation. X2 is equal to S2 minus S2F over S2G minus S2F. It always has the same format. Actual minus F divided by G minus F. Okay, we do have S2F and S2G. Let me show you. We found S2F here and S2G earlier from the table. And we don't have S2, but what is S2? Let's take a look. 1, 2, 2 is a vertical line. That means they have the same x coordinate. So S1 must be equal to S2. And I do have S1. It's equal to S2. Okay, so what we can do is to change S2 to S1. And now we can plug in the numbers. Okay, so X2 is equal to And the solution is 0.9895. That is x2. So now finally I can go back to this equation to look for H2. We do plug and chug. Our solution to H2 is 2741.8 kilojoule per kilogram. So now we're done with H2. And next one, H3. H3, let's take a look at the diagram. H3, we have found H3 already. Right, if you forgot, let me show you. Right here, we found H3 from before, so we just copy down this number. H3 is equal to 3353.3 kilojoule per kilogram. So now we're done with H3. Next one, H4. How do we look for H4? Let's take a look. Number 4 is a mixture. Number 4 is within the dome, so you have to find quality first. Okay, so essentially you're just repeating what you did for number 2. First of all, look for quality. How do you look for quality? Same old method. It's S4 minus S4F divided by S4G minus S4F. Okay, did we find S4F and S4G? Let's take a look. Yes, we found S4F and S4G, so I don't need to worry about those. What about S4? What about S4? Do we have S4? Not really, but let's do this again. 3 to 4 is a vertical line, so they must have the same x coordinate. So S3 must be equal to S4. Did we find S3? Yes, we did. And it is equal to S4. So now I have everything. S4 is equal to S3. So now we can just plug in all the numbers. Our solution is 0.9384. And keep in mind, always give quality x a subscript because we have so many different points. If you do not write a subscript, people wouldn't know which point you're talking about. Okay, so now in order to look for H4, you just use the weighted average equation, 1 minus x4 times H4F plus x4 times H4G. I have x4 now. Do I have H4F, H4G? Let's take a look. Yes, right here. H4F, H4G. I found those two from earlier. So what we do is plug and chug. Oh, sorry, solution here is 0.9382 times H4F, which is 173.88 plus 0.9382 times 2577.0. So our solution for H4 is 2428.5. The unit is kilojoule per kilogram. So this is how you find H4. Okay, finally the next one, H5. What is H5? Let's take a look at diagram. H5, number 5 is point F and it's at the same pressure as number 4. So H5 is essentially just equal to H4F. And do we have H4F? Right here, I have H4F. So I have H5. Okay, and then finally the last one, H6. How do we look for H6? 5 to 6 is the pump, and we always use the same method for the pump. We've done it once, so let's do it again. W dot pump over M dot from first law is equal to H6 minus H5. The bigger one minus the smaller one. The bigger one is H6. And then we also know W dot pump over M dot is equal to W dot control volume work for process 5 to 6. And we learned from before is equal to integral nu dp. Lower limit is P5, upper limit is P6. And now those two must be equal. So H6 minus H5 is equal to integral P5 to P6 nu dp. And now we can continue. Why? Because from 5 to 6, if you take a look at our diagram, from 5 to 6, what is the phase of the working fluid, water? 5 to 6, the whole thing is to the left side of the vapor dome, so everything is liquid. For liquid, density is constant, and the inverse of density is nu, so nu must also be constant. If nu is constant, then you have a constant integrand, so you can pull nu out of it. After you pull nu out of it, you add a subscript. You can call it either nu5 or nu6. And which one do you think you will call it? If you call it nu5, what's going to happen? Nu5, number 5 is F point, so nu5 is just equal to nu F, which can be easily found from the table. If you call it nu6, number 6 is subcooled water, which we don't have a table for. So what we need to do is better just to call it nu5. After you take nu out of it, what is left? It's gonna be P6 minus P5. So from here, we can easily calculate H6. H6 is equal to H5 plus nu5 times P6 minus P5. Okay, let's take a look. H5 I just found from earlier. P6 and P5, those are easy. For example, what is P6? Let's take a look. P6. P6, pressure of number 6, it's on 8 megapascal line. So P6 is 8 megapascal. What about P5? Number 5 is on the bottom constant pressure line, which is 0.008 megapascal. So P5 is just 0.008 megapascal. So I do have P5 and P6. And then the only thing I don't have at this moment is nu5. But like we said before, this one is very easy to find because you're just looking for a nu F. Okay, so what do we know about number 5? We know the pressure of number 5. The pressure of number 5 is 0.008 megapascal, which is 0.08 bar. Then we start from pressure, we go to table A3. And what do you look for in the table? You look for column nu F, and that nu F will just be your nu5. And from the table, you can find out nu5 is 1.0084 times 10 to negative 3 cubic meter per kilogram. So now I have everything in the right hand side. I can just do plug and check. H5 is, okay, let's copy down this equation again first. All right, plugging H5. H5 is 173.88. And make sure you convert unit to joules by multiplying 1000. Okay, plus nu5, 1.0084 times 10 to negative 3. And it's SI unit already, so we don't need to do anything. Multiply by P6. P6 is 8 megapascal, so 8 times 10 to the 6. To convert megapascal to pascal, minus 0.008 megapascal. So we do the same thing, times 10 to the 6 to convert megapascal to pascal. Now, finally, our solution for H6 is 181.94 times 10 to the third, and it must be SI unit, so it is joule per kilogram. And then we do one more step. It's 181.94 kilojoule per kilogram. So now we're done. We found enthalpy of every single point. Efficiency can be easily calculated. The equation we derived from earlier is H1 minus H2 plus H3 minus H4 minus H6 minus H5 divided by H1 minus H6 plus H3 minus H2. So you can just plug in all 6 enthalpies and make sure you use the same unit, which is kilojoule per kilogram, because they will cancel. So our solution is 0.403. If you can recall the efficiency from the previous example, the solution for efficiency was 37%, and now the efficiency has gone up to 40%, all because of the design of reheat. So reheat can actually, yes, increase the efficiency. Okay, so that's part two, look for efficiency. And then part three is to look for mass flow rate. How do you look for mass flow rate? It's always the same. Let's take a look. There's one given condition that we haven't used. What is that? W dot cycle equal to 100 megawatts. This is something that we haven't used. So let's start from here. W dot cycle over m dot, what is that? We actually derived it already. It's just the numerator for efficiency. Remember, if you forgot, you can just go back to our equation here. Our numerator here is W dot cycle per unit mass flow rate. And then we rewrote the numerator into this whole thing. And then we continued, we rewrote the whole thing into this. So this is just the W dot cycle over m dot. So we can just copy the numerator alone this time. Which is H1 minus H2 plus H3 minus H4 minus H6 minus H5. Okay, so now rearrange this equation. Move mass flow rate alone to the left-hand side. Right-hand side becomes W dot cycle over the whole thing. H1 minus H2 plus H3 minus H4 minus H6 plus H5. And we have everything on the right-hand side. W dot cycle is given as 100 megawatts, so times 10 to the 6 to convert to watts SI unit. And then you plug in all 6 enthalpies, H1, 2, 3, 4, 5, 6. And because every one of them has the unit of kilojoule per kilogram, so multiply by 1000 to convert kilojoules to joules. Okay, so the final solution for mass flow rate is 65.65. It must have an SI unit, which is kilogram per second. And that is all for this example.